Okay, now we are going to solve this problem by using solid elements. So let's move to ANSYS Workbench. Our problem is a structure under static conditions, so I'm going to use a static structural. Next, I'm going to open Design Modeler, and in Design Modeler I'm going to import the IGS file of the claw bone. So you can save your geometry in different formats. The one I've used here is IGS. You can use step, for instance, as an alternative. So here's the geometry. I open it here and then I hit generate. So I've now generated the volume, the body here. So next we go to the model to set up the rest of our simulation. Now we are ANSYS Mechanical, we have the geometry, we need to define the material. So as I mentioned, I'm going to use ABS. So if you search for ABS, you see down here under plastic ABS, you can have different types. I'm going to use this type, and when you press this, it will be added to the available materials. And you can look at the properties that ANSYS is using for this ABS, like Young's modulus 2.4 gigapascals, Poisson's ratio, etc. This is interesting. This is the stress strain curve for ABS at different temperatures. Here we are not going to change the temperature, so it will use the default temperature, which is 23 degrees Celsius. But you can see ABS is actually quite sensitive to temperature change. And then here we have the tensile ultimate strengths, which we will use to see if our structure will fail under the pressure. So here this value is 38 megapascals. Next, we need to discretize our geometry with finite elements. So there are different options available to us in terms of the type of elements, as we discussed before. So we can have tetrahedral, pentahedral, like wedge, prism, and we can have hexahedral elements. Let's go with the default and see what ANSYS will use. So you can see ANSYS has used tetrahedral elements, and the order of the elements that it has used by default is quadratic. So you can spot that here. You can see that this edge looks like is broken, which means there is a node here. So it has a node and an additional node on the edge. This edge seems to be straight, but there is another node on this edge, and this edge, and all other edges. So this is a 10-node tetrahedral element that has been used by default. Here you can change other things, like you can change the order of the elements, so you can move from quadratic to linear if you like. That is possible. You can change the default mesh size. You can have more control over the mesh size if you like. You can change the mesh size here as well, and the way that mesh is propagated throughout the structure. Actually, if you go to help, so if you click on mechanical help and search for mesh, you can find plenty of information about how to control the mesh. For instance, here I can add method, and under method I can choose the entire volume, and here I can tell the software to force it to use tetrahedrons. Tetrahedrons are very good for meshing complex geometries like the one that we have here. I can ask the software to try to mesh this with hexahedral elements, but if you try it, you will see that it cannot generate that many hexahedrons, and it will be more made of tetrahedrons. And if you choose other methods, you will see that it will try to use a mixture of the different types of elements that we have seen, those 4 types, to succeed in meshing the structure. The other thing is that you can add sizing, for instance, here. So that gives you more straight control over the sizing. For instance, you see this is the default sizing. It's around 3 millimeters. I can go, for instance, for 2 millimeters, and now I update the mesh. So you will notice that we have now meshed the structure. So you see that now there are 2 elements, for instance, through this thickness here. Previously there was 1. Okay, so by reducing the size you can have more elements, but there is a concept here that is called mesh refinement concept. So essentially you do not refine the mesh forever. You continuously refine the mesh and control the output parameters, for instance the maximum von Mises stress or whatever is the output measure. And when you see that by reducing the mesh further there isn't much change in the output parameter, that is when you need to stop refining the mesh. You can also refine the mesh locally in areas of stress concentration or regions of interest. So that is possible as well. So you can select edges or faces, and once you have done that you can insert sizing locally, and that will locally refine the mesh for you. Okay, what else? We need now to define the known boundary conditions. So here we can choose displacement or fixed support. Both of them will do the same thing. They both will fix or make 0 the translational degrees of freedom, or translations of the nodes of solid elements. You know, solid elements do not have rotational degrees of freedom, so this and this will not make any difference. So let's use fixed. I'm gonna choose the surfaces, this one, this one, this one, and this. Apply. So all of them are fixed. Yeah. So it means that the translations in X, Y, and Z of all the nodes placed on these surfaces will be 0. Next, we need to apply the pressure. So pressure is here. I choose this surface, apply, and the amount of pressure was 100,000 pascals. So what should we monitor? We can look at total deformation, and we can look at different stresses. We can look at von Mises, we can look at maximum principle, and it really depends on the failure criterion that better suits the material. If we imagine or assume that ABS is a brittle material, then we can use maximum principal stress. If we believe that it is a ductile material, we can use von Mises. To be honest, I'm not completely sure what we should use for this ABS. We need to do some search, but I have a feeling that maybe maximum principal stress would suit us, because ABS I believe is more brittle. But still, I would encourage you to do some search for that. You can also watch our failure criteria or failure analysis lecture to understand a bit more what different failure criteria are doing. So now we solve the problem. So when we are solving, essentially what it does is that it is now using the geometry of the elements, and it is forming the element stiffness matrix, and from there it is putting it into equilibrium equation together with the known members of vector of nodal displacement and the known members of vector of nodal forces, do the inversion of the matrices, and then find the field variable, which is translations. And once it's found the field variables, then it uses the equation I showed you earlier to convert the translations into strain and a strain to stress. Okay, so what we see here is the final product, which is stress. So let's first look at total deformation. I believe it makes sense. So this is like a sanity check. When we apply the pressure, the deformation should be like this. and we can look at maximum principal stress. So here you can see the maximum value is 7.3 pascals. So this is extremely small for our problem. So of course this claw is very unlikely to fail under the pressure that we have applied on this face. Well, something else in relation to mesh, you remember that we discussed the mesh quality metrics. So here actually we can look at different metrics. For instance, I can look at aspect ratio. So you see the aspect ratio maximum is 10, minimum is 1.1. We see that some elements do not have a very good aspect ratio, but visually we can see the majority have quite good aspect ratio here. We can look at Jacobian ratio. There are 3 definitions here, so I encourage you to look at the manual, but we can look at the ones at the Gauss points or the integration points. And you can see some are quite small, but still above 0. So I believe ANSYS is recommending that this has to be, is better to be above 0. So nothing negative here, but it can go down to -1. This is how it's been calculated in ANSYS. So you can see some of the elements actually in the area of interest for us, where we saw the maximum stress, have quite low quality. So what we can do is to refine the elements in these regions, just to improve the precision, or in other words, reduce the discretization error in our problem. So interestingly, what we can do here, we can have graphs like this, like aspect ratio graph. So this has now changed to aspect ratio plot, and here I can see which elements have aspect ratio between 1.2 and 2.5, for instance. These are the elements that have 2.5 aspect ratio, within this range, and these are the elements that have aspect ratio within this range, and so on. You can change the bins. So here it has used the number of bars is 10. You can increase it 20, whatever you want. And you can see as well the type of elements that could be available, but in this problem we don't have any of these. We only have TET 10. So you can see, for instance, the ones that have aspect ratio over 5 are these ones, and these are not really in the area of our of stress concentration, so we are not too much concerned about them. But let's look at the Jacobian ratio, for instance, at Gauss points. So you see the majority are close to 1, but there are some that are quite small, like this one, or this one, or this one. So you can see that these are actually located in the area of stress concentration. So I think it would be a good idea to refine the mesh locally in these areas and make sure that we have good quality element in those locations. Well, we can see that here we have stress concentration in this region, but we have only one element. And from the manipulations I've shown you in the theory I've shown you in the lectures, in the lecture related to solid elements, we can conclude that for linear elements, the stress is constant throughout the element. For quadratic, it has a linear distribution. So for such an area of stress concentration, still using one quadratic element is not a good idea. So it's much better if we refine the mesh in this location until we see that this value is converging to a limit. Well, I hope that you have enjoyed the solution to this problem. Thank you for your attention.